When we analyzed circuits before, the first step we usually did was we would find the equivalent resistance of the entire circuit. Now, sometimes that can't be done. If you look at the circuit that we have over here, the reason you can't find an equivalent resistance for the circuit is because of the fact that there is two batteries. If you have multiple batteries in a circuit, you cannot find an equivalent resistance for the circuit. We would use that equivalent resistance to find the current through the battery. Well, here we have two batteries. So what do? Well, what we do is we use Kirchhoff's rules. Kirchhoff's rules come in two parts. They're what's known as a node rule and what's called a loop rule. The node rule is really simple. All the current that goes into a node, one of these guys, equals all the current that goes out of it. In other words, charge isn't being created or destroyed, it's conserved. An example might be if I had a current, let's say this current was 1 amps and it came into this node, it's splitting into two. Those two parts have to add up to the 1 amp that we had going in. Okay, so generally we will write those something like this. In this particular circuit, if you notice, I3 is coming into this node and I1 and I2 are flowing out of it. So I could write that I3 equals I1 plus I2. Now in this particular problem, they've made and labeled the currents for us, but we could do that ourselves. We could have drawn any currents that we wanted to in the three different branches and set it up in equality like this, and that's a node rule. Now the loop rule basically says that the sum of all voltage gains and losses around a closed loop in a circuit has to add up to 0. In other words, if I'm a charge and I'm marching my way around one of these loops, I will gain voltage in certain places, I will lose voltage in certain places, but when it's all said and done, when I get back to where I started, it's going to all add up to 0. Let me do an example. So if I start a loop at this point right here, and I were to go around, you'll see I'm going to go around this outer loop here. I cross a battery, I cross two resistors on this branch that contains current I3, and then when I go over here, I cross another resistor on this current I1. The way to add up the voltages in this circuit is to recognize that you will gain and lose voltage at every battery and every resistor. And there's a trick to it. If you're going on your loop and walking around and you go from the low side to the high side of the battery, you will gain voltage. I think of it, it looks to me like I'm going upstairs, and so if I'm going upstairs, I'm going to gain voltage. So the first thing I'm going to do in my loop here is I'm going to write 45 volts because that's what I'm gaining. Okay, now as I pass across resistors, in the case here, remember voltage equals current times resistance. So I have a current of I3 and a resistance of 1 ohm. So I'm going to write that as minus 1 I3. And the reason it's minus and not plus is because I'm going with the current. We will come across examples where we don't go with the current, and you would make that a plus. And I'll try to do one like that so you can see what I'm talking about later. But all we're doing is crossing these various components in our circuit and kind of accounting what we're coming across. So I started with the battery, I gained 45 volts, I'm going to lose 1 times I3. Now I'm going to go across the 40 ohm resistor and I'm going to lose 40 times I3. The 40 being the resistance and I3 being the current. Okay, now I'm going to cross this node. At this point, I'm now on current I1. So when I come across the 30 ohm resistor, I'm going to lose 30 times I1. And then I'm going to continue around until I get back to the start. Once I reach the place I began, I can write equals 0. So that's my first loop rule. My first loop rule consists of a battery and 3 resistors. And all those voltage gains and losses add up to 0. Now let's do another one. I'm going to switch to another color here. So this time, just to show you how these work when you go against the current, I'm going to start here and I'm going to make this big outer loop right here. So if I start here and I move to the left, as I cross this resistor, I'm going against the current. When I go against the current, I write plus 1 times I2, Why I2? Because that's the branch I'm on. Now I hit the battery. Now here I'm going from the high side to the low side. So I'm going to write minus 80 volts. And then I'm going to come up past this node, go on to I1 again, and write minus 30 I1. Come back around, cross this node, and now I'm going to hit 20 ohm resistor. Now this 20 ohm resistor is on the same branch as I2, so I'm going to write plus 20 I2, and then I'm going to wind up where I started and write equals 0. The loops that I made are totally arbitrary. I decided to start here and go around clockwise. I started to go here and go around clockwise. You could have gone counterclockwise. You could have done any two different loops you want to do. It doesn't matter. You will wind up getting the correct answer as long as you do your algebra right either way. It doesn't really matter how you do it, because as long as you do a good job and a correct job of writing these equations, in the end you will get enough equations to solve for your unknowns. My unknowns here are I1, I2, and I3. So now I'm going to consolidate the terms in these two loop rules. So I'm going to start with this one. I'm going to write it down here. I've got 45 volts. I'm going to drop off the unit at this point and just write it as 45. Now, I have two I3s. I've got 1 I3 and 40 I3, both of them negative. So I'm going to write minus 41 I3, because I'm just going to add them together. And then minus 30 I1 equals 0. And what we see here is that we have two unknowns in this equation. The other equation, I've got, you notice I've got a plus 20 I2 and a plus 1 I2. I'm actually going to put the voltages first. That's just kind of a preference I have. I'm going to write minus 80, and I'm going to write plus 21 I2, and then I have my minus 30 I1. At this point, what you've done is you've created enough equations to solve for your unknowns. I've got an equation up here, the node rule. I've got two equations down here. If you have three unknowns, you need three equations. I have them. Now comes the fun part where we actually do all the horrible algebra that gets us to the answer. I feel at this point we've actually done all the physics that we need to do, but if you want to get to an answer, you have to do some algebra. And there's some methods for doing this that can make your life somewhat simpler. So when I look at these two equations, the pink one has I3 and I1 in it. The green one has I2 and I1 in it. What we'd like to do is get these equations so they only have two unknowns in them, the same two unknowns, and that way we could solve those two equations for an answer. They both contain I1, so it would make no sense to eliminate I1 from either of these equations because we'll still have three unknowns. What I want to do is get rid of I3 or I2. Now if I look up here, this thing is already solved for I3, so what I'm going to do is I'm going to substitute in for I3 I1 plus I2, and let's see what that looks like. So I'm going to make this now 45 minus 41 I3, but instead of I3 I'm going to make the substitution I1 plus I2. Then I'm going to write minus 30 I1 equals 0. At this point I need to multiply this out and combine like terms, so I'm going to have 45 minus 41 I1 minus 41 I2 minus 30 I1 equals 0. And if I combine my I1 terms, I'm going to get 45 minus 41 I2, and I've got minus 71 times I1 equals 0. Now I'm going to take this equation over here and rewrite it underneath. So I got minus 80 plus 21 I2 minus 30 I1 equals 0. And now I have two equations with two unknowns. At this point you can do linear algebra, you can make substitutions, whatever it takes to solve for the answers that you need to do. I don't really want to go into all the algebra required to do this at this point. You could easily solve this for I1 and substitute it in here. You could find common denominators for some of these, though this one would be brutal. You've got a 71 and a 30 and a 41 and a 21. Probably not the way to go. Or you could use a linear algebra matrix to solve for this. What I can do is tell you what the answers are. And the answer for I1 would be negative 0.87 amperes. And for I2, 2.6 amperes. And for I3, see, once you get I1 and I2, you can put them back up in this equation here to get I3. And you would get 1.7 amperes. Now, what's interesting here is that I1 is negative. What does that mean? What that means is, if you notice up here, we've got I1 going kind of from left to right across this resistor. The negative means that it really doesn't go that way. It goes the other way. So the negative indicates direction. And when we first created these currents, or the problem, the book gave me those currents, it's just a guess. And you really don't know which way the currents are going to go. It turns out that their guess that it was going to go this way was wrong. It really goes this way. And that's okay. That's where the algebra will correct you in the end. You can also use Kirchhoff's loop rules to find the voltage drop in any two parts of the circuit. All you would have to do, let's say for instance, you wanted to find the voltage drop between, say, this point and this point. We'll call that point A and point B. It's not a complete loop, but you can still use Kirchhoff's laws to get there. Now what's cool about this is I could go from A to B, I can go this way, or I can go this way. And it doesn't matter which way you go, you'll get the same answer either way. So let's say I wanted to go, I noticed that if I go to the right and up and over, I only pass by two circuit elements. That's probably the easiest way to do it. So I'd say that the voltage difference from A to B is, if you notice here, I'm going with current I2 across 20. So I would go minus 20 I2. And then I'm going to go across this battery from low to high. So plus 45. And knowing I2, I could plug that number in here and I can actually get what that voltage difference would be. Kirchhoff's rules are extremely useful, but they also create very, very long problems. And I only gave you a few of those to do for that reason. You just have to push through. But again, like I said before, that the physics ended when we created these equations right here. That was the end of the physics. The rest of it is just a bunch of fun math.